Welcome to this next video in which we are discussing separable polynomials. Okay, so finally in this video what we're going to do is give a criterion that you can use in the ring of polynomials over the field capital F to determine whether a polynomial f is actually separable or not. Okay, so let's get on with it. So let's say that we've got some polynomial f of x which is in the ring of polynomials over the field capital F. Okay, and we are trying to determine whether this polynomial is separable or inseparable. Now these definitions, separable and inseparable, they're only applied to polynomials that are not constant polynomials. So we are instantly assuming that our polynomial f of x here is a non-constant polynomial. So you've come up with some non-constant polynomial from the ring of polynomials over the field capital F, and it's your job now to decide whether this polynomial is separable or not. Now of course one way to do it would be to actually create the splitting field and have a look using the definition and see, have you got roots with multiplicities greater than 1. Okay, that's one way, that's the most obvious way of doing it, but now what we're going to do is we're going to have a criterion for determining whether this polynomial is separable or not without actually having to construct the splitting field. Okay, which is something surely that we should be able to do because we know that all of the information for the splitting field is encoded in the polynomial. Okay, so surely this concept of separability which comes from the splitting field should therefore be accessible from the information in the polynomial without actually having to construct the splitting field. And indeed it is, and that's what we're about to see. Okay, so here comes this big theorem then, and I'll call it big claim. Okay, so the claim is that we can say that this polynomial f of x is going to be separable over f. Okay, so f of x is going to be separable, and I'll just colour this in, if and only if it is true that the polynomial and its derivative, which is something that you can construct in the ring of polynomials over the field f, are relatively prime. So let me write this down. So if and only if, so they're two equivalent statements, f of x and its derivative, which is something that, as I say, you can construct in the ring of polynomials over the field f. If f of x is from the ring of polynomials over the field f, then the derivative of f of x will also be in the ring of polynomials over the field f. Okay, and we need them to be relatively prime. Now what does relatively prime mean? Relatively prime means that the only common divisors of the two of these, okay, so the only polynomials in the ring of polynomials over the field f that are common divisors for both of these, i.e. each of these is a multiple of that common divisor, are units. Okay, that's what it means for them to be relatively prime. There is no non-unit polynomial in the ring of polynomials over the field f that both of these are multiples of. Okay, so that's what we want to prove, that f of x is going to be separable if and only if you can find its derivative and these two polynomials are relatively prime to one another. And I should just add one little bit here, in the ring of polynomials over the field f. So this is something that you can do just in the ring of polynomials over the field f. You don't need to construct the splitting field. Okay, this is something that you can work out in the ring of polynomials over the field f, which is the huge advantage here. Okay, now let me firstly just make a comment on this right hand side here. So we know that our polynomial f of x here is a non-constant polynomial, so we know it's not equal to the 0 polynomial. However, the derivative of the polynomial could end up being the 0 polynomial. If that is the case, then f of x and the derivative of f of x, which is 0, are not relatively prime. Okay, because 0 is a multiple of anything. In particular, you could write 0 as 0 times f of x. Okay, so the common divisor that you could come up with is f of x, which is certainly a non-unit element because we're assuming it's a non-constant polynomial here. Okay, so if the derivative is equal to 0, then this isn't true. They are not relatively prime. If, however, more normally the derivative is not equal to 0, then what it means for these two to be relatively prime is that you'd have to decompose each of these into their irreducible factorizations, and because we know that the ring of polynomials over a field is a Euclidean domain, we hence know it's a principal ideal domain, and hence a unique factorization domain. So factorizations into irreducibles is unique up to the fact that you can change the associates that you're using of each of the irreducibles. And if you do that, if you factorize f of x and the derivative of f of x into their irreducible factorizations, which you can do for all elements apart from 0, you can do it for all of the units, you just write them as a unit, but for all of the non-unit elements it's more interesting, that's where you actually find the factorization into irreducibles. Okay, if you do that, they will have no irreducibles in common. Okay, the only common divisors that you can come up with are units in these, for these two polynomials if they're relatively prime. That's what it means for them to be relatively prime. Okay, so this is a condition then for this that you can use that is functional just in the ring of polynomials over the field f. So that's lovely because it means you don't have to construct the splitting field for the polynomial over the field f to actually decide whether this polynomial is separable or not. So this is excellent. Okay, so let's now prove this statement, and we're going to prove it using what we've just shown about how if a polynomial has a multiple root in its splitting field, then that will be a root of its derivative as well. Okay, right, so we will start again with the only if portion here, and of course the only if corresponds to this arrow here. We need to show that if this is true, this is true, because if that's the case, then we can say that the only way this can be true is if this is true. Okay, so I want to prove this arrow here, the only if first. So I want to prove that if f of x is separable, it implies that the polynomial and its derivative must be relatively prime in the ring of polynomials over the field f. Okay, so the only common divisor of both of them is going to be a unit. Okay, right, so how can I do that? Well, let's suppose that, yes, we'll start with this starting assumption here that f of x is separable. And now let's do it by a proof by contradiction. So let's suppose that actually the two are not relatively prime. That would mean that f of x and the derivative of f of x had some common factor that was not a unit, i.e. I can write f of x as, let's say, some quotient q of x times this common factor g of x. Okay, so this is going to be the common divisor that is not a unit of f of x and the derivative of f of x that must exist if I'm saying they're not relatively prime. Okay, and the derivative of f of x here will also be writable as, let's say, some quotient which I'll call q bar of x times g of x there. Okay, so this polynomial g of x, I know that it's not going to be a unit. I also know that it's not going to be the 0 polynomial, because if it was the 0 polynomial then that would imply f of x was the 0 polynomial, and we're assuming f of x is non-constant. Therefore I can conclude that these two polynomials here, the polynomial g of x is a non-constant polynomial. So f of x and the derivative of f of x would have some non-constant polynomial in common, basically. Okay, they will be writable as multiples of this polynomial in the ring of polynomials over the field capital F. Now, why is this a problem? Well, if you now go up to the splitting field K, which is a field extension of F, then of course in this splitting field, the polynomial f of x will have to split down. So in particular, g of x, this factor of f of x, will have to split down into linear factors. Okay, but then if we look at the derivative of f of x in the splitting field, g of x will also split down into the same linear factors as it did here, over here, and that will mean that there will now be common roots to both the polynomial f of x and the derivative of f of x. Okay, and we know that whenever you've got a common root of f of x and the derivative of f of x, that implies that that root is a multiple root of f of x by the previous theorem, and therefore that will contradict f of x being separable, which was our starting assumption. Okay, so we have now proven that it must be the case that if f of x is separable, that f of x and the derivative of f of x are relatively prime, because if they're not relatively prime, you can prove that they're not separable. Okay, excellent. So we've now proven the only if. Now let's go for the if. Okay, so let's go for the if, and the if, of course, is this arrow here, We want to prove that if it's true that f of x and the derivative of f of x are relatively prime, then it's also true that the polynomial f of x is separable. Okay, so how are we going to do that? Well, again, we're going to do it by proof by contradiction. We're going to assume that this, of course, is our starting assumption. So we'll assume, yes, that f of x and the derivative of fx are relatively prime. And now we'll assume the opposite of what we want to prove. We'll also assume that f of x is inseparable. Okay? Now, what does it mean if f of x is inseparable? Well, it means that there must be a multiple root for f of x. Okay, so there must exist an alpha such that alpha is a multiple root of f of x in the splitting field. But we know that if alpha is a multiple root of f of x in the splitting field, then alpha is both a root of f of x and the derivative of f of x. So there's going to exist an alpha is an element of the splitting field, k, such that, and I'll just move this up a little bit, if you evaluate f at alpha, it's equal to 0, and if you evaluate the derivative of f at alpha, you also get 0. Okay, so that's what it would mean if the polynomial f of x was inseparable. We're now going to use this to find some contradiction. So we're going to contradict that these two are relatively prime, basically. Now, think about this. Alpha is an element of the splitting field k, which is a field extension of f. And f, we know, is a non-constant polynomial, so it's in particular a non-zero polynomial. So I've got some non-zero polynomial in the ring of polynomials over the field f, which has alpha as a root. That means that alpha is algebraic over f. So alpha, which is an element of the splitting field k, is an algebraic element over the field f. Okay, now what does that mean? Well, we know whenever we've got an algebraic element over a field f from our study of algebraic field extensions, we know that that means that there is some minimal polynomial for alpha over f in the ring of polynomials over f. So we'll call this, in our normal notation, the minimal polynomial m for alpha over the field f. So the coefficients are going to be in the field f, which is some element of the ring of polynomials over the field f. And remember, this is the single, unique, monic, irreducible polynomial with alpha as a root. So it's the only monic, irreducible polynomial in the ring of polynomials over the field f which has alpha as a root. And we prove in the video on algebraic field extensions that such a polynomial will always exist for any element alpha which is algebraic over f. Okay, what we also prove in that video is that any other polynomial in the ring of polynomials over the field f that has alpha as a root is a multiple of the minimal polynomial for alpha over f, i.e. it's in the principal ideal generated by the minimal polynomial for alpha over f. So I can now conclude that because both of these polynomials, f of x and the derivative of fx, have alpha as a root, that both of them are elements of the principal ideal generated by the minimal polynomial for alpha over f. So f of x is in there, and the derivative of f of x is also in there. Okay, now why is that a problem? Well, this contradicts f of x and the derivative of f of x being relatively prime, because the minimal polynomial for alpha over f, that will be some non-constant polynomial, because it's not going to be the zero polynomial, and it's not going to be any other constant polynomial either, okay, because obviously any other constant polynomial would not actually have alpha as a root, okay, and it wouldn't be the zero polynomial, because that's, you can't apply irreducible to that. Indeed, you can't apply irreducible to any constant polynomial. So the minimal polynomial for alpha over f is always a non-constant polynomial. So this is a non-constant polynomial, and I'm now saying that f of x and the derivative of fx are in the principal ideal generated by this non-constant polynomial. So f of x is a multiple of this, and the derivative of fx is a multiple of this. This is not constant, okay, so they are both multiples of a non-constant polynomial. This is a common divisor for both of them, okay, and it's not a unit. So it contradicts the two being relatively prime. Okay, so what I have now done is proven that if the polynomial is inseparable, i.e. it has a multiple root in the splitting field, then that contradicts f of x and the derivative of f of x being relatively prime in the ring of polynomials over the field capital F. So you can conclude that if the two polynomials f of x and the derivative f of x are relatively prime in the ring of polynomials over the field F, that means that f of x is separable. Okay, so that is a nice place to end. We now have a beautiful condition for when this polynomial f of x, which is in the ring of polynomials over the field capital F, is going to be separable. Okay, you just need to take its derivative and ask, are these two things relatively prime? Now note, you might get the derivative is equal to 0, and as I say, that means that they're not relatively prime. If you get the derivative is equal to 0, then they're not relatively prime. Okay? So you can't conclude that f of x is separable. But if you do get a derivative that is non-zero, then what you can ask is, are those two polynomials relatively prime, i.e. is there only common divisors? Are there only common divisors units in the ring of polynomials over the field F? And if that's the case, then you can conclude that indeed f of x is separable. So that's a lovely condition now for working out whether a polynomial is indeed separable.